But before that happens, we're going to learn quite a bit about some baseball analytics. So I'm very happy to introduce, you've already seen him speak, you've already heard about him. He's a stat geek who's not athletic and so is trying to make himself relevant by scraping NFL data. But here he is again, the legendary Ron Yurko.
Good afternoon, everybody. And so for our first speaker in our baseball session, we have Gregory. He's a statistics professor at Loyola University of Chicago. He's a PhD from University of Connecticut. Previously, he's a 2014 Kaggle March Madness winner with Michael Lopez, and then as well in 2016, Sabre Analytics Contemporary Analysis Award with Ben Balmer and Shane Jensen for their open war paper, one of my personal favorite research papers, actually, as I said. But, and he's going to be giving a talk on research that recently was in the 538 popular website by Nate Silver. Take it away, Greg.
All right, so if there's two things you can talk about at a sports analytic conference that are really going to get people furious with you, I suppose one will be talking about the idea of clutchness, and the other one will be the idea of a hot hand or streakiness. So I'm going to talk about hotness or streakiness, and then if you invite me back, maybe I'll have some work on clutchness. Off the top of my head, yeah, sure. So the orthodoxy, if I talk to you about hot streaks, the sort of orthodoxy in sports analytics is that hot streaks don't exist. And the sort of origination of this idea was a paper by Tversky in the mid-1980s where they were looking at free throw shooting. And then when you actually go read that paper, you realize that it was 1985, and the data they're actually working with is a very small sample. They were looking at like one team, and then they set up an experiment with I think it was Cornell's varsity basketball team, and they were sort of restricted by the era that they were in 1985, and they concluded that there's no evidence of hot streaks. Okay. I could have done the whole thing. So then this has sort of been, people are ferociously against the idea of hot streaks in sports, right? In 1993, Albright had a paper where they looked at streakiness in batting, and they said that some players exhibit the streaky behavior, most don't, and none over this 4-year period studied. And then you start to see a series of papers that are coming out more recently, and they're now sort of flipping the whole idea of streakiness doesn't exist on its head, right? They're sort of saying they have found something that might be considered streakiness. And I think most of these bottom two ones are both basketball related, but Rob and I decided to look at streakiness in baseball, right? So the other thing you need to think about here is, what does it even mean to be a hot streak? So in that Boxkotsky, is that how I pronounce it, paper? They're talking about what is even meant by a streak or the hot hand, and depending on how you define this, you can sort of get you can reach different conclusions. So what we're going to say is, the hot hand is, or I guess in our case it's the hot arm because we're looking at pitching, but we're going to define this as a prolonged performance above or below what's expected for an individual player. Okay? So if you're looking at some sequence of data for a player, if there's a stretch of time where they're performing above what you'd expect or below what you'd expect, we're going to consider that to be that's exhibiting streaky behavior or hotness and coldness, or it's possible it could be you're healthy or you're injured. But there is we're looking for evidence of some kind of streakiness. So what we did is we focused on specifically fastball velocity. All right. What's really nice about fastball velocity is that among things that are measured in sports, quite often there's a lot of confounding factors. So if I'm shooting a basketball, if I'm taking a three-pointer, it's being contested, and we don't know this. There's all these other factors that are related to whether the person is going to make the shot or not. It's like in football is even crazier, right? You could have a sack that occurs because the cornerback 20 yards down the field was covering well, and so it's hard to view things in isolation. But fastball velocity is essentially almost entirely controlled by the pitcher. There are external factors like whether there's runners on base or how many pitches you've thrown and things like that. But for the most part, pitch velocity is being entirely controlled by the pitcher. And so it's a nice stat to focus on because it's so controlled by sort of one source. And we also know that fastball velocity is a good source of a good proxy for performance. There was an article by Fast, I think this is a Fangraphs paper, where he was looking at the relationship between fastball performance and its the faster your fastball, you have it's associated with lower ERAs and lower FIP and several other performance-related metrics. I mean, it's not surprising, right? A faster fastball is better than a slower fastball. That blow your mind? All right. So what we're going to look at here is we're not claiming this is like the perfect model to fit here. We're just saying let's try to fit a model that. What would a model look like if there was streakiness, and specifically two states, hot and cold? What if pitchers were hot and cold, and how would we even go about finding that? All right. So we're gonna look at these things called hidden Markov models, and they're useful here because we have observations that are correlated even within their state, and we're assuming that there's these two states, hot and cold. All right. We're not saying this is the absolute best model to fit here, but we're saying if hot and cold states do exist, let's see what this model set tells us. Okay. So the hidden state here is going to be whether the pitcher is hot or cold, and the emissions that we're observing are fastball velocity. And I'll explain where we're actually using the residual of fastball velocity from a first model. So the way I explain this to, if you've never heard of what a hidden Markov model is, what we're trying to do is imagine that you take Clayton Kershaw and you clone him, and there's Clayton Kershaw hot and Clayton Kershaw cold. And you're viewing the field, but there's a curtain set up, and Kershaw's behind the curtain and he's pitching. That's how to pitch. He's pitching, and you can see the fastball that comes out of it, and you see how fast it goes, but you don't see whether it's hot Clayton or cold Clayton. All right? So we're observing the fastball velocities, but we don't see if it's hot or cold Clayton. We want to figure out, based on the fastball velocity, was it hot Clayton or cold Clayton, and how often does hot Clayton switch to cold Clayton, and cold Clayton to hot Clayton, and so on and so forth. That's the Markov piece of this. Okay. So instead of fitting one hidden Markov model per player, so we could have taken the sequence of fastballs for an individual player over the course of a season, and we could have fit a hidden Markov model individually to all of those players. But you're sort of limiting yourself to only the data of one player. So what we did was we actually took every pitcher has a chain of data, and we took all of those chains of data, and we did what I'm referring to as a mixed hidden Markov model. All right? So I don't know if that's the exact right way to talk about this, but so we're going to come up with league average state means, so the two means hot and cold. We're going to come up with a league average for how different those hot and cold states are. And this is across the whole league. So this is like, within a season, it's like something like 200,000 fastballs. So we're going to use all that information, and we're going to pool it together and see if we can find a difference in states. But we're also going to allow for pitchers to have their own individual emission distributions. We're also trying to estimate one transition matrix for the whole league, so like an average transition matrix. We're also allowing that transition matrix to vary player by player, right? So we're trying to leverage all of the data together across all pitchers across a league in a season to come up with sort of an overall streakiness or an overall model for what the whole league looks like as a whole. All right, that's what we were attempting to do with this. So what we first did was we fit a model because we don't want to use raw velocity. We want to use velocity above what's expected for a pitcher. So to do this, we fit just a simple model where we controlled for effects like elevation, temperature, which does affect fastball velocity, the number of pitches a pitcher has thrown, whether there was runners on base. And then we have a random effect for the pitcher. So we're setting a baseline for each pitcher, and then the data that we're actually going to use is saying how much faster was this pitch relative to their average pitch. right? So if we see a string of pitches that were all several miles an hour faster than their baseline, we're going to consider that to be a hot streak, okay? So we then took the residuals of that model, and we fit this hidden Markov model, a two-state hidden Markov model with these sort of random effects. We fit this in JAGs in R. Okay, so I'm going to skip the technical details, but they're here if you want to see them in the slides. Here are our results for the state means for hot and cold across the league. So this is the average mean of a hot. It's the average. It's the mean of all the pitchers from a hot state, and then the bottom is the mean of all the pitchers in the cold state. So we're seeing here a difference of about it's like 1.7, 1.8 miles per hour between hot and cold on average. And you'll notice from year to year, from 2015 to 2016, it's almost exactly the same. Those are totally separate data sets, and we see almost exactly the same difference in the states. I have 2017 here, but I'm not going to show results from 2017. We've run it, but we believe there are still there are some data cleaning issues with the 2017 data, so I'm not going to present 2017 results, which is disappointing because Baseball World Series is happening right now, and it'd be kind of nice for me to show you something from 2017. These are our transition matrix estimates. So the red box plots here are the posterior distribution of these parameters. It's a box plot of the posterior distribution of the probability of going from hot to hot, and on the bottom, the blue, it's the posterior distribution of going from the cold state to staying in the cold state. These are the red one is like around 95%, and the one down here is around I think 6% or something on the bottom here. This is an indication that there's across the league as a whole, there's a lot of evidence that pitchers are streaky. If they're in a hot state, the next pitch is likely going to be also from a hot state. And likewise, if you're in a cold state, you're likely to stay in a cold state. Now, is this really hot and cold? I don't really want to make that claim, but it could just be that it's injuries. Right? It could be that they're injured or there's something happening that is lowering, that's creating these strings of times where their performance is lower. Right? We're observing this. So here are some of the individual players. So we have these sort of overall means of the hot distribution and the cold distribution, and these are the differences in the hot and the cold distribution. These are individual players. So this is the overall plus that individual players component. And these are box plots of the posterior distribution for that individual player. And these are the largest differences between hot and cold. You'll see a guy like Cologne here has a fairly large difference between his hot and his cold state. But I'll show you a picture. Cologne is actually not a very streaky pitcher. Okay? We're observing a large difference between Cologne's states of hot and cold. But when you actually look at I'll show you this picture, it doesn't look like he's very streaky. It looks like it's, because we fit a model of two states, it's forcing itself to find two states, but he doesn't really have one. So what I'd like to do in the future is try to come up with a model that allows for some players to have two states and then some players to only have one, or allow each player to have an individual number of states, which would be a much more interesting model. It's more complicated. So you see Sale is here, and you see again in 2015, Sale and Cologne are also at the bottom. But these guys end up being not streaky pitchers. They just have a lot of variability in their fastball velocities. This right here is a picture of the fastball velocities, the residual of the fastball velocities for Bartolo Colon in 2015. There's a pink line and a blue line, a light blue line, and those are the means, the overall league means of the emission of the means of the hot and cold state. The red line and the blue line are the averages for the individual player here. But what you'll notice here is that there's not really many streaks here. He's transitioning back and forth between hot and cold, and this doesn't look like there's any evidence of streaks. And there are players who we're observing that simply are not streaky, right? And Bartolo Colon, it doesn't look like there's any real pattern to his fastball velocities. It doesn't look like there's any at all. And we observed the same behavior from 2015 to 2016. I'm sorry. This is with residuals, and this is with actual fastball velocity. So they're showing you slightly different things, but you can see about the same behavior. I hope it's obvious, where the circles are red, that's where he's in a hot state, and when the circles are blue, he's in a cold state. And there are actually purples where it's uncertain which state he's in. This is the posterior probability of being in the hot or the cold state. But when we look at a guy like Clayton Kershaw, we see something different here. We see very clear streaks. Kershaw is actually one of the streakiest pitchers in the league. And we see very distinct patterns of streakiness. So these black lines represent their individual games. So all the fastballs that Clayton Kershaw threw in that first game, from the first black line to the second game, it looks like he was in a cold state most of that game. But you'll notice that it looks like there are games where Kershaw it looks like he's having hot games and cold games. And in the data that we're using, we're not even distinguishing where the game starts or ends. We're just it's one string of fastballs. It's like it's picking up on something that's happening here. And it looks like there are these games where he's having streaks of hotness or coldness. This is 2015. We also have his velocity for 2015. It looks very similar. But there's definitely some streakiness that's happening here, or how I would define streakiness. And you observe the same behavior in 2016, right? There looks to be these hot and these cold streaks in 2016. And at some point in I don't know, a laser pointer, but he was injured in this year and he came back. And I believe he had 5 starts after he was injured. And you can see there's a big dip in sort of 5 starts in. There's a big dip in his coldness, and then there's a big gap in he didn't pitch for, I think, a few months in 2016. So one possible direction for us is to look at trying to line this up with injuries, because we don't really, we're not entirely convinced that this is it's not like the pitcher's just trying hard. We're not convinced that that's it yet. We think there's something here, but we don't know if it's injuries or what is actually causing all of this. But we are observing some streakiness in pitchers, and other pitchers we're not observing it. Okay. And here's Clayton Kershaw in 2016 with fastball velocities on the y-axis. So you can see again that he's definitely exhibiting behavior that is much different than Bartolo Colon in terms of his fastball. Okay, so the big question is that, great, you've fit this model, you've sort of forced a 2-state hidden Markov model onto this data, and you can retrospectively decide whether a pitcher was hot or cold. All right, but the real test here is can we predict anything going forward? So that's a really good question. So what we wanted to do is we fit a model. So ideally, how we would do this is we would fit a model on time n1 to n, and then we would predict time point n+1. We would re-estimate from 1 to n+1, estimate n+2. That's very computationally intensive. So we did something a little bit simpler. We took the first 2 months of 2016, so April and May, and we fit the model only using that data to estimate the transition matrices and the emission means for all the players and the transition matrix for all the different players. We then took that, and that defines a hidden Markov model, and we can then run the Viterbi algorithm, which is going to decide which state you're in. It's going to make a prediction about what state you're in. So we run the Viterbi model using the estimated parameters. We're using the means of the estimated parameters. We run Viterbi from time 1 to n. We then make whatever the prediction is at time n. Right? If we predict they're hot at time n using Viterbi, we say, all right, our best prediction for going forward, it's whatever state you were in previously. So we're predicting the next state with the parameters of the model fit from the first 2 months of the season, but then we're using the actual fastball velocities that we observed in the Viterbi algorithm. So we have this string of fastballs from like June, and we're using that string of fastballs to decide whether you're hot or not in the next state, right? So when we do this, we then have a prediction that is only using previous data. So we're only using data from time 1 to time n to make a prediction for the next pitch, for the next fastball. So then we can say, all right, we have a prediction. Let's see what performance looks like in those next pitches, whether they're hot or cold. Let's see if there's a difference between the hot and the cold state. So the two things that we looked at were game stats. So let's look at the last few pitches of a game. So we looked at the last 5 pitches. This is really simple. We looked at the last 5 pitches of a game, and we saw what the prediction was. So there's 5 different predictions. It could have been hot or cold, hot or cold, hot or cold, and we counted how many times you were hot in those last 5 pitches. Like 85% of pitchers are going to be all hot or all cold, but there are times where there's like 3 hots and 3 colds. So we were looking at those last 5 pitches, and then we wanted to see how that related to the next game's performance. And so what we actually find is that the hot pitchers, on average, if you were in the hot state, and this is relative to yourself and relative to what the projection was for that game. So we used steamer projections to predict how many strikeouts a pitcher should have had in the game, right? Because you want to factor in your opponent and all these different things. And then we compare it to what actually happened. So we have how much better were you in the actual game versus what someone projected you to do. And we actually find that the pitchers who are hot are, on average, getting about 0.4 more strikeouts than pitchers who are cold. Right? And this is all based on, it's all prediction, right? We're using only data that came before this. We also find that the ERA in these games is 0.87 runs lower for the hot pitchers than the cold pitchers. Okay? I think those are really. I'm comparing a pitcher who had 5 hot pitches at the end of a game to a pitcher who had 5 cold pitches at the end of the game. This last piece I think is really, really interesting, and I can't really explain this. But we also looked at pitches, so we can predict. Let's look at all combinations of pitches where they throw a fastball and then a curveball. And we can predict whether that fastball is going to be in the hot state or the cold state. And then let's look at the next curveball that was pitched. We actually find that even though curveballs are a very different pitch from a fastball, we actually find that the curveballs after a hot fastball are breaking slightly more than when the fastball is in a cold state. I think that's really interesting. Looks like it's time to go though.
Time for questions.
You're creeping.
We keep finishing. Good?
Okay, that's basically it.
Okay.
So my conclusions are, I really believe we found something here. I keep trying to tell myself, all right, there's got to be something we're missing, and maybe we are, but I think we found some kind of streaks here, whether it be injuries or whatever it is. I think we found something. I say, is it really hotness or coldness? I'm only using those terms because I'm trying to anger you, I guess. I don't know. I'm trying to make a lot. But it might just be that we're seeing injuries or something like that, or there could be, pitchers may take days off, right? But it looks like there's something happening here for some pitchers. And we do have evidence that this is predictive. Hot pitchers who are hot now seem to perform better, slightly better when they're hot than when they're cold relative to other projections for some baseline. And also, I'll put a huge asterisk on this. There's still a lot of work to do on this. This is sort of like something I'm doing on the side. I have a real job, I guess. And I think there's a lot of different directions to move in that could really, really improve this. But I'm definitely not going to stop doing this. I do think there's something here. Cheers.
When you said about the curveball drop changing, did that control for anything like base outstate or count? Because if you're coming from a hot fastball, maybe you're more likely to be in a better count and then more likely to try to spike the curve.
We did control for other things. I have to look that up to get you the actual answer, but I can look it up if you really want to know. We did control for. There are several things in that model, so it's not just the break in the curveball as a function of hot and cold. It's hot and cold controlling for a few other things. We were looking at sliders too, but we're not ready to present that, and we have to control for handedness and something like that in a slider, because it's doing different things. All right.
Would the starting pitcher's mile per hour decrease later in the game than early in the game?
So we controlled for pitch count. So it's the residuals that we're coming up with are the residuals from a model where we're controlling for pitch count. And so as you throw more pitches, your velocity on average decreases. And so we're controlling for that a little bit. It's possible we should have had a player-specific. You might need a player-specific term for how they change, because different pitchers degrade with pitch count differently. I'm not sure how much our results would actually change, but maybe it's something we should consider.
And wouldn't the pitcher's velocity in a full windup be faster than from the stretch with a runner on
Yep,
base?
that's also, we also control for that in our model. If we have a variable for whether there's a runner on base versus not on base. Yeah, absolutely. Those are good points. Yes?
Yeah, I'm just confused. Why would you choose to look at pitcher streaks when, at least naturally, the way I would think is you want to focus on hitter streaks? Because that seems to be what managers and people always worry about a hitter breaking up their streak. Like, when a pitcher seems to naturally is going to have a natural way to break a streak, which is their a starting pitcher at least 5 days rest.
Why would we focus on hitters rather than pitchers?
No, pitchers rest.
Why would we focus on, is that what we did? Why would we focus on pitchers rather than hitters? I don't think there's anything here for hitters. So we've actually looked, we've tried to do something with batted ball velocity. So we're looking at velocities off of the bat, and we really aren't finding anything. Hitter streaks are also much more difficult because it's affected by the pitcher and the type of pitch, and there's much more to control for, so it's a little bit harder to find. So we looked at pitchers because pitchers are easier? Is that a reasonable answer? I think we gotta go.
Stop there, and thanks, Greg, again.